This is a LEGO freight train. And these are 5 more LEGO trains that we want to run on the same track at the same time, so they can all make their deliveries fast. Oh yeah, and we want them to drive themselves. The only problem is, these trains are still the regular clueless kind. So, let's build them some brains.
Our trains need to travel between these 6 cities across the United States and Canada. So we'll start by turning our living room into a railway network that connects them all, using LEGO train tracks and switches. And we'll lay it out the way real trains run across North America, just tiny. With Kansas City in the middle as a major hub where everything meets.
So, getting this freight train from Calgary in the north all the way to New York City requires some navigation. If we make this first switch track straight and the second one diverging, the train should take the correct tracks to get to New York. But if the CSX wants to get from Los Angeles to Atlanta, which it does, it needs to flip these 2 switches. And if it can't, it'll never get there.
So our first job is to make our switch tracks switch themselves. Which means that first, we need to hook up a motor. We're going to use LEGO PoweredUp hubs and motors, just like the ones in the motorized LEGO Technic sets.
This switch design uses what's called gearing down. We use a motor to turn a small 12-tooth gear, which then drives a bigger 20-tooth gear, making it easier for our honestly pretty weak motor to push this fairly chunky switch. So now we can write a tiny program to flip our switch using Pybricks, which is an amazing work of free open source software that lets us run our own code on LEGO hubs. We'll tell our hub to spin the motor for a fraction of a second to flip the switch. It should spin clockwise to make the switch diverging, or counterclockwise to make it straight. Right now, we're just telling the switch to switch itself every 3 seconds. And we'll do the same thing with our other 9 switches. Each switch gets flipped by 1 LEGO motor, which has to be hooked up to a LEGO hub. Each Technic hub has 4 ports, so it theoretically can power up to 4 motors. But between LEGO's optimistic cable lengths and our layout spanning the width of a continent, we'll need 5 separate hubs for our 10 switches.
So now that our Python code is running on each hub, we should never have to use our hands to toggle any of the switches. Okay, that's enough.
Now for the CSX to get to Atlanta, we need to coordinate multiple switches. So let's introduce one more hub to be the leader. This thing is going to act as the big boss program for everything else. This way, every switch can just report its position to the big boss whenever it changes, and listen for commands from the boss to know when to switch. And all we need to do is talk to the boss. We're going to use the LEGO Inventor hub to be the leader, because it runs a little faster than the other types of hubs, but this should also work with a LEGO Technic or City hub. Plus, we get these shiny lights. The boss program will issue all its commands on one channel, and each switch will report its status back to the boss program on a different channel. When the boss sends commands, it'll say the name of the switch it's trying to talk to, so all the other switches can ignore it. And we'll send a command number too, so that each switch can write down which numbers it's already handled, so it doesn't execute the same command over and over.
This all uses Bluetooth to communicate wirelessly, using hub-to-hub broadcasting in Pybricks. So now we should be able to type commands here, to the leader. And all the switches move the way we tell them to. And the leader knows where everyone is. But controlling the track isn't very helpful if we can't control the trains.
So, tucked away inside each of our trains, we've put a powered-up city hub, a train motor, and a color and distance sensor. So to get this to run autonomously on our layout, we're going to need to color code our track layout. That way the trains can use their color sensors to find out where they are. We're going to use 4 colors of tiles, because beyond that, our LEGO color sensor starts getting a bit creative with its color guessing. But since we have more than 4 track segments to work with, we need to do a little encoding. By combining our colors into stripes of 2, 3, or 4, we can get up to 20 distinct patterns. We only need 6 of them for now, 1 for each city, but we'll use the rest once our tracking gets fancier.
We would normally spend weeks lurking around the LEGO store picking up people's dropped pieces for these parts, but thanks to our patrons, we can just order them on LEGO.com. And after waiting at the door for a week for our LEGO package, which definitely made it arrive faster, we can use our new LEGO tiles to label our track segments with our new color codes. By the way, instructions for building all the trains and the cities in this video are linked in the description if you want to build your own. And all the code in this video is available on GitHub.
And now that the track is fully coded, we can program the train. This works just like the switches did. We can just tell the motor to move forward and backward at a specified speed. So for example, we can make it move forward at 45% of its top power until it sees red, and then move backwards until it sees blue, and then stop. And the Big Boss program should control the trains too. We want to be able to broadcast a command like CSX run until you get to yellow-green, or CN run backwards until you get to yellow-blue. So we'll send commands and receive status on different channels, just like the switches, but with a slightly different format. And we'll add some logic to detect color patterns instead of just single colors. The LEGO color sensor is also pretty unreliable and does things like report red in the middle of yellow or report purple even though there's no purple anywhere. So we need to add some logic to filter out any noise or wrong readings. So we'll only count ourselves as seeing a color if the color sensor sees it 2 times in a row. And now we can say, hey CSX, go to yellow-green. And it gets to Atlanta. Or, hey CSX, go backward to green-red. And it'll get back to Kansas City.
So now, we need to put all this together in the real world to have the trains actually go where we need, without us helping them navigate.
To do this, we need to implement what's called pathfinding. This is how Google Maps tells you how to get to the park, and how UPS knows how to route delivery drivers to get to everyone's houses. Let's first turn our real-life train layout into something our code can understand. To do that, we divide our track up into 2 parts. The important places, like our cities, which we'll call nodes, and all the tracks and switches connecting them, which we'll call edges. This is what's called a graph in graph theory. And since LEGO switches only switch if the train runs from the straight side of their Y junction, we need to keep track of which direction the trains travel in. So we'll actually draw 2 arrows for each track piece, one going forward and one going backward. This is what's called a directed graph. We can think of it like a roadmap where we've marked all the possible ways the train can move. And with this, we can implement an algorithm to find the shortest path between any 2 cities. So in our case, LA and Atlanta. We'll start with an algorithm called breadth first search. We start from where our train is, at Los Angeles. And then we imagine taking one step in each possible direction. So from LA, we can move to Calgary, to Kansas City, or to Las Vegas. And then we just keep doing that. So from Calgary, we take one more step in each possible direction, so we can get to Kansas City or New York. Then we explore from our second branch to Kansas City and see that we can move to New York or Atlanta. And Atlanta is our goal. So we found a 2-step path to get to Atlanta. This is called breadth first because we look at all the 1-step paths first, then all the 2-step ones, before we get to longer paths. It looks simple, but it's guaranteed to find the shortest path in terms of number of steps between any 2 cities, if there is one. So let's implement this in Pybricks really quick. First, we translate our real-life track layout into code. So we're saying there's a track segment between LA and Las Vegas. And the same for LA to Calgary, LA to Kansas City, and so on. We'll also define the color codes for the end of each segment, and which switches need to be flipped for the train to travel on each segment. And once we have the train layout as a graph, we can translate the breadth-first search technique we showed into a set of steps that we run over the entire track. Oh, and by the way, we also need to track which direction the train is moving, which we handle with these reverse for lists. These define which direction our track segments point in. And now, we can see if it actually works. We want to be able to tell our leader, hey, send the CSX from LA to Atlanta. And it should figure out which switches to flip and tell the train where to go and when to stop. And we can ask the leader to send it to Kansas City just as easily.
Cool, it works! But what happens if we go from Los Angeles to New York instead? It got there, but going to Canada in between doesn't seem like the best path.
The problem is, the path the train is taking right now works, but it isn't always the shortest. There's actually a much more direct path between LA and New York going through Kansas City that our train is completely ignoring. So to fix this, we need to add distances to our train layout. For each track segment, we can count how many LEGO studs the LEGO train has to travel over. And we'll change the algorithm we're using too, to use our new distance data. So instead of breadth first search, we'll switch to something called Dijkstra's algorithm. Think about how water flows downhill. If you pour water at the top of a hill, it doesn't just take any random path down. It always finds the shortest way to flow to the bottom. Dijkstra's algorithm works kind of like that. Instead of exploring just one segment at a time, like we did before, we let our search flow outward based on actual distance. So from Los Angeles, Las Vegas is only 100 LEGO studs away, so we reach it first. Then Kansas City, at 200 studs, Then Calgary is even further, at 224 studs. It's like dropping a stone in a pond and watching the ripples spread out. The ripple hits closer things first, and then gradually reaches further and further out points. Now, instead of routing through Calgary, our algorithm chooses the more direct path through Kansas City to New York. Both routes use 2 track segments, but by measuring the actual distances, our system can see that one path is significantly shorter. Let's try that on the real hub. We add our distances in LEGO studs to our graph data, and then implement Dijkstra's algorithm ourselves. The most important part of the implementation is this special queue we'll make. Instead of using a first in, first out queue like we were doing before, which would blindly send us to Calgary first, just because it was first in line, we'll upgrade to something called a priority queue. This lets us be smarter about our choices, and pick Vegas over Calgary because it's closer. So we implement that here. And the rest of the pathfinding is almost the same. And now,
Nice! Now we don't go all the way to Canada to get between LA and New York. So the train can get itself between any 2 points. But what if now we add more trains?
let's try loading the same Pybricks train code we wrote earlier onto each one. We can tell each train its destination, and it'll route itself there, but it doesn't work because the trains don't know about each other yet. We need to improve our boss program so that it can coordinate multiple trains while keeping them away from each other, but still efficiently moving toward their goals. Now, we're starting to get into how real railway systems work, just at a smaller scale. Let's say that today, the CSX needs to travel from LA to New York, the Union Pacific needs to travel from New York to LA, the Canadian National needs to travel from Calgary to Atlanta, and why not, the BNSF needs to travel from Kansas City to Las Vegas. I think we can make our pathfinding algorithm do this, as long as we add a few improvements first. We're gonna want to add more precise position detection, sort of like adding more radar checkpoints to an air traffic control system. So specifically, we want to know when a train is approaching the end of a track segment, just before it gets to a city. That way, we could have one train almost get to Kansas City, but stop just before it. So a second train can depart and leave the city free. So we can use most of the color codes we still have free to tile the ends of each segment, approaching each city. We also need to add train safety zones to stop trains from getting too close to each other. And one last problem. Now that we're handling multiple trains, our problem is computationally a lot more difficult to solve. And our boss program is running on this tiny LEGO hub, which is honestly a really, really slow computer compared to the magic devices we use today. So to make sure we don't run out of time or memory trying to coordinate all these trains, we need to make our pathfinding smarter. Think about how you plan a road trip. If you're looking at a map trying to get from Los Angeles to New York, you don't consider every possible road the same amount. A road that heads south towards San Diego, for example, probably doesn't look great, because you have to travel some distance on the road to get there, and also, once you get to San Diego, New York looks even further away than when you started. This is how an algorithm called A* works, and this is exactly what we're going to have our LEGO hub do. Instead of exploring every possible path like before, we'll look at each potential move and think about two things. First, how far will we have actually traveled so far? And second, how far away does our destination still look after the move? If we add these together, we have a pretty good guess about whether this path is worth exploring. So if we're trying to go from LA to New York, if we go through Las Vegas, we'll have gone 100 LEGO studs, and New York looks about 236 studs away, so total score is 336. And going through Kansas City, we'll have gone 200 LEGO studs, but New York only looks about 128 studs away, so total score is 328. The lower score wins, so we'll try Kansas City first. This way, our traffic controller can be smarter about which paths to explore first. It's like having a good sense of direction, rather than just wandering around randomly. And this makes our program much, much faster, which means our hub hopefully won't freeze up when computing the route. So a little bit of programming later,
Now, these trains are kind of smart. They find the shortest route, but avoid conflicts with other trains, and plan reversals when needed, all while constantly updating their plans based on where every train actually is, not just where we think they should be. But what about 5 trains? What about 6 trains? What if we thank our patrons for making this video possible? What if we add another city? Or 3? Wait, what happened to Boris? Please post your challenges in the comments, and we'll try and make the trains do them. And if you want to learn how to build these trains, watch this video next.